Okay, our next speaker is Khalid Muhammad Al-Fuwail. He will be presenting a paper Renewable Power Generation, Maximization for UAVs with Adaptive Sliding Mode Control.
Okay. Greeting everyone. My name is Khalid Muhammad Al-Fuwail. I am an undergraduate student who is studying a bachelor degree at KFUPM University of Petroleum and Minerals. And now I am presenting to you what I have come up with during the last 3 months. It's about the maximization of the UAVs, which stands for the Unmanned Aerial Vehicles. Okay. The UAVs is considered as one of the most used cutting-edge technologies in various applications. And these applications includes surveillance, rescue, delivery, and the military uses as well. But the most important question is, do they really fly at their maximum duration with high efficiency? I mean, there is a limited battery life that restricts the flight time and mission range, and also the high power demand due to the onboard sensors and communication systems, because the UAVs is autonomous, so it requires more sensors, more computers, and many systems that work autonomously. And these systems require more battery consuming. So this will restrict the UAV's ability to fly. And there is a need for an extra power generation for these UAVs to extend the flight durations in the critical missions, especially in the military missions. So we in King Fahd University of Petroleum and Minerals, there is an international competition for the UAVs. US 2030, this is the team that we created to participate in this competition, and we secured the first place in this competition. One of the flight tests that we conducted is to measure how our UAVs were consuming the power. So here, this graph shows the results that we obtained from the autopilot. Inside the computer, inside the drone, gave us a result of the flight information. So we have from 6:40, we conducted the flight for 7 hours. We make the UAV flight for more than 1 hour with turning on all the systems inside it, including the sensors, including the cameras, the actuators, and etc. And during all these times, we have measured the GPS speed, the speed of the drone, because the drone gave the speed at certain positions, and the battery energy. So we noticed that the energy keep increasing, the consuming keep increasing, which is a proof for a need of an extra power supply for the UAVs. So we propose implementing a small turbine called Ram Air Turbine. It is just a small turbine in the UAVs that take advantage of the high wind speeds that faces the UAV. So the Ram Air Turbine will implement it here inside the drone, and it consists of the PMSG, Permanent Magnet Synchronous Generator, the regular PMSG, and with 3 high phases currents, and also the pulse starts with modulation rectifier to convert it to DC, and the rod and the controller that we will explain it later, the proposed controller. But we ask ourselves an important question, does this turbine work at their maximum performance? There is a study that called Innovative Ram Air Turbine that studied or showed the performance of the Ram Air Turbine and their power supply. It's the study was measured the electric power, the shaft at 35 feet above the ground, and the electrical power, the maximum one, was about 150 kilowatt. Okay. What's the paper that we have come up with propose enhancing this turbine by what? By a controller, and the controller is the sliding mode controller. Okay. First of all, let us see the inputs of this Ram Air Turbine. This graph shows the speed that the UAV faces. We have used the anemometer, a device that measures the speed of the wind that faces the UAVs. And that's the graph. All of that was implemented using MATLAB, of course. And here is the structure of our proposed controller inside this turbine as well. We have the turbine blades. It gives a rotational speed to inside the system. And here we have a high-speed shaft because the rotational speed that the blades give is small. We have to increase it. And after that, it goes to the PMSG to convert it from a mechanical energy to an electrical energy. And it is connected to a converter side, to generator side converter, in order to make it suitable and stable for another uses like storage or integrating it with smart grids, of course. And we have the DC link. It works as a buffer to regulate the voltage later with the space vector pulse width modulations. And the PMSG gave the power production, and we have here the current neural network that gives information to the sliding mode control. We will explain later the purpose of each one as well. First of all, the sliding mode control measures the rotational speed that is given to him to enhance it, because this controller has shown itself to be better in handling the disturbances and uncertainties, because the wind has a nature of fluctuating. So this controller has proved itself better than the PID, better than the model predictive control, better than any controllers in these applications. And we have here a line updating below, because the tape ratio speed is important, and it is a crucial factor for extracting the power from the wind. So at each point of the wind, we have to measure the tape ratio speed, and the online updating law will keep calculating this tape ratio speed at each time, and give it to the recurrent neural network. The recurrent neural network, the purpose of it was to see the uncertainties of the dynamics of the turbine itself. So each uncertainty happens to this system was given to the sliding mode control, because it has a closed loop. It will do a corrections for the errors. Okay? And this is the result that we obtained. The PMSG rotary speed was per second, as you can see, for 40 seconds. All the graphs will be shown in 40 seconds, because this experiment was implemented using a MATLAB. The future work later will be implementing it as hardware to get benefit of it in future UAVs or drones applications. And we have here the turbine PMSG torque that directly controls the turbine performance, and it is vital, of course, for adjusting the power generation under different wind conditions. And here we have the turbine speed. It is similar as the PMSG speed, because they are connected to each other. And we have here the turbine power. The power produced was about 400 kilowatt, according to our results in the Simulink, in the MATLAB. And if we remember, in the previous study, they come up with the previous study was implemented as hardware, and it gives power generated as 150 kilowatts. So it is 4 or 3 times more than the previous study. And this is the laws that we used in the simulate to obtain this result. We have the power production, which is the half the air density and the radius of the plates in the wind, the speed of the winds, and the coefficient of the extraction, and the pitch angle and temperature speed. Temperature speed is given by this rotational speed in the radius over the speed. And we have here the power control gain given by this law. And it is here for the optimal power generation. Okay, this is the structure of the RNN that we talked about it before. It is we have the input layer as the rotational speed and the power generation, and we have here the hidden layers as shown here, and the activation function, mode activation function, and it gives the D hat, which is the prediction of the uncertainty. And this is the result of the RNN in the MATLAB itself. As we notice, for the first 25 minutes there is a diverge. Why there is a diverge? Because the uncertainty was high. Because in the regular or normal applications of the wind speed was normal. It was about 5 to 6 to 8 meters per second. But when we talk about the UAVs that faces a high wind speeds, the uncertainties and the disturbances in the wind itself become more huge, because we are talking about high wind speed, like 35 meters per second in a very high height. Okay, so the first there is a diverge, and then there is a converge for around 30 to 40 seconds, which is of course proved the system, the improved system control. And the conclusion, the proposed system using adaptive sliding mode control with RNN-based uncertainty estimation improves the power extraction by 4 times compared to the normal Ram Air turbines in the previous study that I showed before, even in high nonlinear environments. So if we be able to implement this approach as a hardware, and I will show later how to implement it as a future work, we can get next new generation of UAVs that depend on itself in producing a power while it's flying. Imagine UAV generating a power from the wind, from the speed of the wind that it faces automatically. So it's a renewable power inside one of the most cutting-edge technologies that's used in our world right now. And of course, the future work is to implement it as hardware, as I mentioned more than one time. And for example, we can use the STM32 microcontroller running the sliding mode control algorithms. And regarding the RNN uncertainty estimation, we have the Jetson Nano and the DBS. This is a high technological computer that can run an AI in real time. So we can use it and connect it to the STM32 inside the UAV itself. And we can put inside the UAV and turbine, a regular wind turbine connected to all of these systems to improve its efficiency. And of course, this implementation in the real world application will give us a new challenge that we will face later, that we did not consider before. So it's something good. And finally, I would like to acknowledge my university, King Khalid University, under the Research Center of Aviation and Space Exploration, and also I would like to acknowledge the US 2030, the team, our team that participating in this global competition for providing their flight data that I have shown before. And that's all. Thank you so much. And this is those the authors. Thank you very much. Does anyone have a question?
Floor is open for questions, please.
I think first picture is the handsome one in camouflage.
What?
The handsome one was the first picture.
Thank you so much, Doctor. Thank you so much.
So may I ask one question? Yes. Have you considered the efficiency and the cost in your study while using this
You mean the cost of what exactly? Clarify more.
I mean, after the simulation, you are trying to say that in the future you will demand.
Yeah, it's hardware, yeah.
Yeah,
Inside
yeah.
our project, because we will participate again in this competition, so we might implement a lot of things.
Okay,
And one of it is the
Have you
turbine.
considered the cost, how much?
No, we did not have.
Yeah.
But our university will support us, especially in this application, because our university showed us very interest in the work of.
How about the efficiency? Have you improved the efficiency a little bit or any percentage?
All the experiments were conducted using a MATLAB, so it's just a visualization.
Still, you can estimate the efficiency.
Another question?
Like, I'm not quite get well understand of what purpose are you using the neural network for. So you please show us the last slide.
Okay. Which
The last one.
this one?
I think the last,
Yeah.
the summary. The last.
The last summary.
Summary?
Yeah.
So this one.
Yeah.
So you mentioned that the RNN method is used for
Uncertain estimation.
anticipate the uncertainty estimation.
Yeah.
If you get the uncertainty information, and then how do you use this?
What's the purpose of using that, right?
Yeah.
Okay. Imagine happens a sudden change in the wind nature. Because the wind nature, we don't know it. It keeps fluctuating. Imagine that there is a sudden change happens in the wind itself. How this system that I proposed will handle that? And if it keep repeating one again and again and again, how this system will handle it? So we need an approach or a model that can learn these changes by time and train upon it. So if it happens again, the controller, because it is a thermal controller, is just a closed loop controller. So we'll learn this change before it happens or during it happening. So it will learn how to handle it.
So you use this estimation for real-time control.
Yeah, real time.
But this estimation will take you 30 minutes, 30 seconds
30 seconds.
for doing that. But after you get the estimation, 30 seconds later, so is it enough for you to take real-time control?
Yeah, it's more than because the computer can do huge things, and it's very fast. I believe, yeah. But the MATLAB showed you something, and maybe the real world will show something else. So it is under consideration.
But it still takes 3 seconds for estimate, right?
Yeah, I can show you. This picture can clarify more. This one, right?
Maybe
This is the answer.
I understand. So it take about 30 seconds to get an accurate estimation, right?
Yeah, so maybe it will take 25 seconds sometimes and sometimes, because in the simulink I input the wind speed to be varying.
Oh, you input the wind at the record time, and you get estimation 30 seconds later.
It keeps together. Like, how can I explain it? Let us assume that this is the estimation of my system, or my approach, right? And this is the real one, as it can show here. It keeps tracking until it learns how it's behave. You understand me? Like at the beginning, there is a huge divergence because this is the beginning. We begin the flight. or we begin the mission, or we begin the action.
Yeah.
Okay, so there is disconnection, but by time it will learn. So it keep getting approach. It will keep getting to each other until it reaches this one. So after 40 seconds, I make it for 40 seconds. I make it in the MATLAB. I put the time range unto 40 seconds. But in the real world, when they keep moving, it will be like this.
For MATLAB,
This is the
it's
mistake.
possible, but for the real application, you use the windage 30 seconds before, right?
30
So
seconds.
the computation need you 30 seconds
Mhm.
to accomplish. So you input the date, you get the result 30 seconds before, afterward, and you control. So
Yeah.
after 30 seconds later, the wind will change.
It is changing. The controller is tracking it. It's changing at the beginning. It understands how it's changing. You understand me?
Okay, we can talk
Oh,
later in the
okay.
practice, maybe.
It's tracking it. Like for example, okay, discuss later. Okay. Any questions? Thank you so much.
Okay, thank you very much.
Hold on a second. This is for my universities.